Hello APC Mechanics students, in Unit 3 Work Energy and Power, Class 4, 3.1 Forces and Potential Energy, Part 1. Now Section 1, Conservative Forces. Forces admit several classifications like contact versus non-contact forces, as we have seen in Unit 2, or even fundamental versus non-fundamental forces. Another important classification is conservative versus non-conservative force. A conservative force F is a force that can be derived analytically from a potential energy U using the relation Fx is minus du by dx, where U is the potential energy associated with the conservative force F. So here what I'm trying to say is that a force is said to be a conservative force if it's being associated with a potential energy U. Now what's the relation between U and F is that F is the derivative of U with respect to x. Notice that here the derivative is with respect to the position and not the time parameter t. So basically all of the previous definitions, derivatives that we have defined previously are related to the parameter time, which is responsible for the evolution of the system. Here we're defining a conservative force with respect to a potential energy via a derivative, but the derivative with respect to the position. Then any force F that admits a potential energy U is considered to be a conservative force. Example of some conservative forces are given by the pull of gravity, gravitational force, the tension in the spring, whether it's linear or non-linear, and the electric force Fe. Not all forces are conservative forces. Example of some non-conservative forces would be friction of all types, kinetic, static, or even the drag force. These forces cannot be represented by a potential energy. Now Section 2, work done by a conservative force. Let F be a conservative force. So the moment we say that F is a conservative force, it means that it can be derived from a potential energy. Using the following relation, we will assume that this force only has a component along the x direction, that is F is Fx. Now if this force have other components like along the y direction, then Fy also would be given by minus du by dy. We are interested in calculating W, which represents the work done by this force in moving an object from an initial position to a final position, and this can be defined as an integral. Now this dot product can be written as follows. Now F dot dx would be the x component, for example, plus the y component, or simply let me say, because we have assumed that F is only along the x direction, then this can be written as and here we assume that both vectors are in the same direction, so that is Fx dx. And now Fx can be replaced by the negative derivative of the potential with respect to x. Now remember that this is understood as an operator on one hand and as a fraction on the other hand, so this can be simplified with this, and we're left with the integral of minus du. Now the minus can be dragged out, and now we're gonna implement the identity. Now remember that if we're integrating dx, that would give us simply x, because here we have 1. If we're integrating du, that would give us u. Now here if we set the boundaries between initial and final, so let me write it here. If we're doing from an initial value to a final value of dx, that would give us delta x. For this reason, because we're integrating u from an initial value to a final value of du, that would be delta u, which means that the work done by a force, if this force is a conservative force, can be written as the negative change in the potential energy, and we know that the change is given by u final minus u initial. Now what does this mean? Which means that the work done by a conservative force is independent of the path followed and only depends on the initial and final state of the system. Now this result is very important. Why? Because first of all, our problem only consists with initial and final position. We assume that the force is conservative, and the result is that the work done by this force is the negative change in the potential energy. So which means that if we know the potential energy initially and finally, that would allow us to calculate the work done by force, and pictorially can be represented by as follows. Now suppose we have an initial position to a final position. If we're dealing with a general force and we need to calculate the work done by the force F to do a work from the initial position to a final position, this can be only done if we know the force itself and the path along which we're doing the force. So basically the displacement, because this will be expressed as an integral from an initial position to a final position given by f dot dx. So this requires from us to know the force explicitly as function of x and to know the displacement that we're moving along. However, in case where the force is a conservative force, then the work done by this force is independent. How do we go from the initial position to a final position? So let me say that this is a path going from initial position to a final position, and this is another path, this is another path, this is another path. So in brief, we can take an infinite path that relates the initial position to the final position, along which we can calculate the work. And this work might change if we choose, for example, the blue path compared to the black path. However, if our force is said to be a conservative force, it is independent of the path followed and only depends on the initial and the final position of the system, as has been stated here from this relation. So let me say, which means that the work done by a conservative force is independent of the path followed and only depends on the initial and final state of the system, which is represented by UI and UF. Alright? Moreover, conservative forces have a direction pointing where the potential decreases the most. Now this statement is very important. Later I will refer to this statement during the exercises. Another thing to add, conservative forces are more to be considered as forces that would serve as an operator to conserve energy and transform it completely from one form to another. Unlike conservative, non-conservative forces would transform one form of energy to another, and this conversion is associated usually with the dissipation of energy, which is known as heat, in which this type of energy is hardly reversible. Now let me summarize the different properties of conservative forces that we have discussed so far. A conservative force is usually associated with a potential energy U via calculus. The work done by conservative force is independent of the path followed and only depends on the initial and final state of the system via the relation. So WF would be minus the change in the potential energy, which is UI minus UF, because this is minus UF minus UI, and that would give us UI minus UF. The variation in the potential energy can be calculated using the following integral. The change in U is minus WF, which is minus the integral that we know. Conservative forces always have a direction that points toward or where the potential decreases the most. Conservative forces convert one type of energy into another without any loss. Now, section 3, potential energy of a Hookean spring. Springs, when compressed or stretched, they store energy. In particular, this form of energy is elastic potential energy. The force responsible for storing this elastic potential energy is the tension in the spring. The aim of this section is to determine the expression of the elastic potential energy stored in a Hookean spring. Now, because we have mentioned previously that the tension in a Hookean spring is a conservative force, so we can ask the following question: what is the potential energy associated with the tension force in the spring? Now let's consider a linear spring stretched from the equilibrium position by an elongation x. So here we have the spring that has been stretched by a displacement x from the equilibrium position. For a Hookean spring, the tension force, which is the restoring force, is given by minus kx. The elastic potential energy can be determined using the relation delta U is minus the work done by the force, which is minus from the initial position to a final position F dot dx, where the initial position in this case is the equilibrium and the final position is the elongation x. Replacing in the above integral we get, so delta U would be the U final minus U initial, minus the integral, so yxi is 0 because this is the equilibrium position and the final position is given by x. Now F here has been replaced by minus kx. Now minus or minus will give us plus. Ui corresponds for the potential energy stored in the spring and the equilibrium, which is 0, no elongation or compression. Then here what I'm trying to say, what is Ui? Ui is the potential energy stored in the spring at this point. And here, when the block is at this point, this corresponds for no elongation or no compression, which means that the spring is unstretched, and which gives us that the potential energy in the spring is 0. For this reason, that would be replaced by 0. And now we can perform the following integral. K is a constant, can be dragged out. Then that would be kx squared divided by 2 from x to 0, where x is the elongation, and that would give us kx squared over 2 minus 0. Then the elastic potential energy stored in a Huygens spring when stretched or compressed by distance x from the equilibrium position is given by us is half kx squared. And here, if you notice carefully, this potential energy represents only the potential energy stored in the spring if it is elongated. Now why here I mentioned whether it's stretched or compressed, simply because x has been raised to the power of 2. So if we're doing the compression, that would be minus x to the power of 2, and the minus sign would cancel with the even power. Now section 4, graphical interpretation. Previously we have interpreted the area bounded by an fx curve to be the work done by the force F. Now here we have F versus x. Then the area under the curve would represent the work done by the associated force. The work done by force F is Wf is related to the change in the potential energy. Delta U is minus Wf, which yields to the following. A positive area means a positive work, which means that the change in the potential energy delta U is negative and the potential energy decreases. Now first of all, let me say the following. Delta U is the change in the potential energy. If delta U is positive, it means that Uf minus Ui is positive, which means that Uf is greater than Ui, which means the potential energy increases. If delta U is negative, this means that Uf minus Ui is negative, which means that the final potential energy is less than the initial potential energy, which means that it decreases. So the increase or the decrease in the potential energy can be interpreted from the sign of delta U. If delta U is positive, this means that the potential energy increases. If delta U is negative, this means that the potential energy decreases. Now how can we know whether the potential energy increase or decrease by referring to the area? Because we know that the area might be positive or negative. For example, if we refer to the following graph, here the work done is negative because it's below the horizontal axis. Now we know that delta U is given by minus Wf. So if the area is negative, this means that W is negative, which means that this is positive, which means that the potential energy increases. So let me read it again. A positive area means a positive work, which means that the change in the potential energy delta U is... Okay, here we're talking about the positive area. So let me discuss the case of the positive area. If the area is positive, which means the work is positive, which makes this overall negative. So delta U is negative, which means that the potential energy decreases. However, if the area is negative, which means the work is negative, which means that the change in potential energy overall is positive, and this means that the potential energy increases. More importantly, so this is one thing as a graphical interpretation. More importantly, the force and its potential are related via calculus, so via the derivative, and we know that the derivative is interpreted as the slope or the tangent of the slope of the tangent, which means that the force is the negative derivative of the potential energy, and the derivative always and forever is interpreted as the slope of the tangent. By that, we can say the negative slope of the tangent to a ux graph is equal to the force Fx corresponding for this potential. Now let me clarify more. Here we have a graph. What does this graph represent? This is u as function of r. Now here, whether it's r or x, that's perfectly the same. It's position. Now we can say that the force along the r component is given by minus du by dr. Now, what does this operator graphically represent? So let me take this to be solely. It is the derivative of u with respect to r, which means it is the slope of the tangent to the curve, which is u. For example, if you want to calculate the force at a specific position between r0 and the double of r0, so we can take this point, which corresponds to the following point on the graph. Now here we can draw a tangent that touches the curve at only one point. This is a straight line. We can calculate the slope. Then the force F at this specific position, let me say it's 3 over 2 r0, would be equal to the negative of the slope of this tangent, which has been represented here. Okay, let me give you another example. Suppose we need to calculate the force at r0. Then what do? We draw a tangent to the curve at this particular point. Now this is a straight line. We choose 2 points. We can calculate the slope. Then the force, which is a variable force, but we're computing this force at r0, would be equal to the negative of the slope of this line. Okay, then basically for the graphical interpretation, we're interested in 2 things. We're interested of the area bounded between the f function and the x-axis. This is on one hand. On the other hand, if we have u versus r, then the slope to this curve would give us the magnitude or the force itself. And now we can solve some exercises. A certain one-dimensional conservative force is given as a function of x by the expression F is minus kx cubed, where F is in newtons and x is in meters. A possible potential energy function u for this force is, now we know that the force is related to the potential energy via a derivative with respect to the position. Now here, if we have f and we need to determine u, we need to do the integral, but an easier way to approach this problem is to check which of the following choices, whenever we derive it and multiply it by a minus sign, would give us the expression of f. If you look at choice D, let's try now to derive it. Du by dx, that would be d by dx of 1 over 4 kx to the power 4, and that would give us kx cube. Adding a minus sign here because f is given minus du by dx, that would give us the expression of the force because f is given by minus du by dx, then D would be the correct answer. Exercise 2. A specially designed spring is stretched from equilibrium to the distance x to the distances x given in the table above, and the restoring force F is measured and recorded in each case. What is the potential energy for the spring when it is stretched 3 meters from the equilibrium? Then basically, if we need to determine the potential energy, we need to use the following relation. Delta U is given by minus the work done by the force, which is equal to the minus the integral from an initial position to a final position of f dot dx. Now delta u would be given by u final minus u initial, so let me write down that u final minus u initial would be the integral minus the integral of xi to to xf of f dot dx. However, here we don't have the expression of f in order to integrate. If you notice carefully and try to notice a pattern in the values relating x and f. So when x is 0, f is 0. When x is 1, f is 1. When x is 2, then f is 8. So which means that if we take this to the power of 3, that would give us 8. Now this also works here. 3 to the power of 3 would give us 27. 4 to the power of 3 would give us 64, which means that the force F is cubic in position up to some constant K, and the value of K is 1. Now after we have determined the expression of F given as x cubed, let's check if this expression gives us perfectly the results. When x is 0, f is 0. When x is 1, f is 1. When x is 2, f is 8. X is 3, f is 27, so on and so forth. Now we can replace f by x cubed. Now here, we are not sure whether this expression of f is the magnitude of the force or its restoring form. Okay, so our answer would be correct up to a minus sign. However, I'm telling you this is the magnitude and not the restoring form. Now we're lucky here because all the choices are positive, so no need to worry about the minus sign. This is one thing. Another thing, you can think about the problem as follows. Now they're telling you that we're stretching the spring, so we're moving away from the equilibrium position. Away means that the work would be negative. Negative work, according to this relation, means that the change in potential energy would be positive. So delta U is positive. Then this is positive, okay? Now what about the initial potential energy? If our initial position is the equilibrium, we know that at the equilibrium, the spring stores no potential energy, so this is 0. If this is positive overall, which makes U final to be positive, so our answer is positive, whether we have a negative or a positive answer. Now that would be negative the integral of x cubed dx from the equilibrium position, which is 0, to a final position, which is 3. Then that would give us minus x to the power of 4 divided by 4 from 0 to 3. And that would give us negative 81 divided by 4. And the unit of U, which is energy, is in joules. Now why here our answer is negative? Simply because we didn't take into consideration the negative sign due to the restoring force. Now if I add here the minus sign, minus and minus would give us plus, that would be plus, and the correct answer in this case would be C. Exercise 3, which is an exit ticket for today's class. The above graph represents a hypothetical potential energy curve for a particle of mass m. If the potential energy function is given by that, which of the following is an expression of the force on the particle? So this force is a conservative force because it's being associated with the potential energy, and the force can be directly determined from the potential energy via calculus derivative, not with respect to time but with respect to position. Then we can say that Fr would be given by minus du divided by minus du over dr, which is understood as an operator minus d by dr of b r to the power minus 3 over 2 plus c. Now that would be a constant 0. Now this constant is saved, it will be dragged out, so d by dr of the power function. Now we drop down the power, which is negative 3 over 2, that would be 3 over 2b, and we decrease the power by 1, then minus 3 over 2 minus 1, that would be minus 5 over 2. So r to the power minus 5 over 2, and the correct answer in this case would be A. Then that's it for me in this video, guys. See you soon in a new one.